Wasabi, you guys. Welcome to Integration B Training for Intermediates Part 8. This is probably going to be the starting of the most difficult topics, and that is, in this section, Advanced Trig Manipulation. This is where maybe I might even mess up the most. Yeah, and it's trig manipulation comes in a lot of different ways, either by identity or by conjugation. Algebra, it's a mess. It gets into a mess super easily. So I think it's best if I just dive into our first integral. Now look at this. This is what on earth do we do here? So let's try to simplify everything as much as possible. Let's simplify as much as possible. Now, if you do not know your trig identities, now is the best time because nothing gets easier than this. So we have sine 2x. We know our trig identity. I'm gonna abbreviate mines, right? 2 times sine cosine, and then here 1 plus cosine 2x. There's many identities for that. So which one do we use? I'm pretty sure it doesn't really matter which one you use. I think it'll result the same way. For me, I'm gonna use 2 cosine square minus 1 just to get rid of this 1 and this 2. And then we have secant square. Okay, so now we have, let's see, so this cancels out, and one of the cosine cancels out. Okay, so this is the ln of tangent x. Secant square. Ah, I know what's going on now. So this is just u equals tangent of x, which gives us the integral of just ln of u. So we know that integral, u ln of u minus u. So that means our answer is just tangent of x of ln of tan x minus tangent x plus c. Okay. Here, I would do let sine square equal 1 minus cosine square. Right, I'm just going to abbreviate it again. 1 minus cosine square. And we have 1 plus cosine. Then we can go ahead and algebraically factor this out. So this is 1 minus cosine, 1 plus cosine, 1 plus cosine. This cancels out. We're left with this. And so now 1 minus cosine of x dx. This is the integral to x minus sine of x plus c. Okay, cool. That's all we have to do. What now? That cosine is at the bottom, not the top. So we can't easily do a u substitution. So what do we do here? Well, I'm gonna go ahead and do multiply cosine of x top and bottom. So we have cosine on top. And then we have cosine square, which is 1 minus sine square with square root of sine of x. So 1 minus sine square with the root of sine. So let u equal sine of x. Then we get 1 minus u square square root of u. So now what? What do we do here? Well, because we have this square root of u at the bottom, I'm going to let w equal square root of u. And what this would do is this gives me u equal w square. And so if you do that substitution, you should be left off with 2dw 1 minus w4. If you remember our algebra manipulation or partial fractions, this is the most annoying part, for sure. So, with partial fractions, we have 1 minus w squared, 1 plus w squared. I'm just going to skip to it. When you do partial fractions, you should end up 1 plus w squared plus 1 minus w squared. So this is what you should get when you do partial fractions. I'm just kind of cutting to the chase here. So after that, then this is just equal to inverse tangent. And inverse tangent of w is equal to square root of sine of x. Plus, what is this? This is inverse tang. Inverse tang. And the square root of sine of x. Wow. That, just this integral here, just turns into this monster. So, trig manipulation will always be like this, in most cases. And it can be, most of the time, it can be very nasty if you don't know what you're doing. So, what most people would do, I mean, sine squared plus cosine squared is equal to 1. So we'd rather have that, right? So that's going to give us dx 1. Oh, I'm sorry, no, 4. 4 times 1. That's just 4. And then, because we used up 4 sine squared, we have 5 sine squared left over. Okay. But I do not like this way because then you have this nasty 5 to deal with. 5 is not a square number, and that's just it's a pain to deal with. So let's kind of back up a little bit. So I don't want to simplify it into 1, right? So then what do we do? We're going to utilize this cosine square. So what are we doing is I'm going to multiply secant square, top and bottom. So this gives me secant square. And then this is just 4, and then 9 tangent square. Oh, okay, so then now this is just u equal tangent x. And then we get du 4 plus 9u squared. Okay, so now it's just this. This is a lot easier to deal with, rather than whatever we had, and that was just disgusting. So this is a lot better approach. So now let's see, to deal with this, it's just like before. I want to get rid of this, just to make my life easier. So we get 9 over 4u squared. And so now this is just, first of all, this constant here. And then here we do our, so this is 2/3. If you remember your not really an identity, but it's one of those integral tables. But it's this. And so now this is just equal to 1 over 6 inverse tangent 2 tan x over 3 plus c. Okay. Another common integral for advanced integration bees. This is an annoying to deal with. People would see, oh, this is like sine 2x. Oh, okay. Let u equal, well, I don't know, maybe sine square. And then du is 2 sine x cosine x. And then they have to turn this into like, in terms of sine squares, and it gets disgusting. Don't do this. Do not do this. This is a trap. Do not do this. Don't do this. Do not do this. So, we're gonna do the same thing again. We're gonna conjugate it. So, I like to deal with tangents and secants. They're just a lot easier to deal with. So, let's go ahead and convert these in terms of tangents and secants. And to do that, we just, in this case, we're gonna multiply top and bottom by secant to the power of 4. So, multiplying secant 4 here, that's gonna give us tangent 4. Then of course secant 4 here, that's just gonna be a 1. It just cancels out. But now what does it look like when we multiply secant to the power of 4 here? We get tangent x, we get a cancellation, and then we get leftovers of secant square. Ah, this is so much easier. This is just u equals, well, tangent square. But to make it look easier, to see what's going on, when you do u equal tangent x, you get this, which is another easy u substitution. That's a 4, and this is, it's pretty much this. When you let w equal u square, right? So this is just half of inverse tangent. Then w is u square, which is tangent square, plus c. So this is the answer we get. Okay? Oh yes, a very easy one. I think you already guessed what this is. We just do dx. This is 2 cosine square minus 1. This all becomes half of secant square. And this is just simply a half of tangent x plus c. Oh god. So what do we do here? So there are a lot of ways that people solve this. Most commonly, a lot of people would do like so they kind of like split an integral into 2 integrals or something. It's nasty. The textbook way is to use Weierstrass, but we have not covered that yet, and we won't do that here. Not yet, at least. What I'm gonna show you, my favorite trick, is to use the G-main way. Let me show you how the G boys do it. So, now, in India, they came up with this very cool solution, and I just can't unsee it. And it all comes from a simple constant. Multiply top and bottom by root 2 over 2. And then you get root 2 over 2 here, plus root 2 over 2 here. Now you're probably, asking, okay, why on earth are we doing this? Well, the reason is because if you remember your trig identity, there is this, x plus pi over 4. If you simplify this, you get sine of x times sine pi over 4, that's root 2 over 2. And then plus sine, cosine, sine. Yeah, cosine of x times root 2 over 2, because sine pi over 4 and cosine pi over 4 is, they're equal to root 2 over 2. So, now that we have this is the same thing as this, right? So, pretty much we have root 2 over 2, and then this whole thing is equal to this. Can we change it to cosine, actually? Because I don't want cosecant. I'm more comfortable with secant. So we could actually check, actually. So cosine of, we would have to use x minus pi over 4. Because cosine, sine, sine. Cosine, sine. Yeah, that works. That works. We just have to use minus because the signs alternate for cosine. Okay, so then this means that we could just substitute this to here, right? And this would give us secant of x minus pi over 4 dx. This is super easy because this is just a linear, let u equal x minus pi over 4, that's just dx, right? Oops, don't delete everything. Don't delete everything, that's not what I want. So, here, if you remember your integral of secant x, this is equal to root 2 of ln of secant x minus pi over 4. I probably should have written it this whole portion here. Root 2 over 2, and then we have ln of secant x minus pi over 4 plus tangent of x minus pi over 4. Right? I'm too lazy to simplify all this. I'd rather just leave it like this. So, this is our answer. And this is so much easier than doing it Weierstrass or any other manipulation. It's so easy, you could literally just see this in your head. That's how amazing the solution is. So what do we do here? So again, most textbook problems, the way they solve this is to multiply top and bottom by secant to the power of 4. And what that would give you is secant 4 here, secant squared cancels that out, and then we get tangent square here. And then you get secant square of x, 1 plus tangent square over tangent square, and then you do u substitution, and then yeah, you get that. But just like in the previous integral, I like the G-main solution, and that is it's a very cool solution actually. This is 1. That's 1. What does 1 equal? A lot of things actually. Sine square plus cosine square. Now you can split this up, and what this does, when you split it up, let's see, if you split it up into two terms, let's see, sine squared cancels out, cosine squared cancels out. Oh wow, this is just the integral of secant square plus cosecant square. That's all it is. Now this is just equal to tangent of x minus cotangent of x plus c. Oh god. Do you remember your trig identities for this one? Because I certainly do not. What do we even do here? Let's see, dx, sine, 2 sine cosine. Okay, so we have 2 sine square. Ooh, if I multiply top and bottom by cosine, then I get cosine square, and I could turn that in terms of sine. Yeah. So this would be 2 sine square, 1 minus sine square. And then with u substitution, let u equal sine of x. And this is just some sort of partial fractions. Okay. We'll take that route, just to be safe. So we have this now. So what do we do? Well, this is 1 on top. Right, if I kind of rewrite this, this is pretty much 1 du. I like to do minus u squared plus u squared, and that's good because here this cancels out and this u squared, this cancels out. Awesome, this turns out very nicely. So now this is just 1 over u squared plus 1 over 1 minus u squared. And with this, you know how we lazy people do, we just use inverse tanch. So this is half of, let me go use inverse tanch first. inverse tanch of u. U is equal to sine of x. And then minus a half of, well, 1 over sine of x plus c. Or this will just be a half of cosecant x. You just write it like that. So this would be our answer. What do we do here? I don't know what to do. What to do here? If we try to factor this out with cosine x, we get 4 cosine square minus 3. What do we do? What do we do with that? What on earth do we do with that? What can we do with that? What is this? What? Cosine? I don't know. 4 cosine square. Let's see. If we think of it as cosine of 2x, right? If that's what we need, multiplying 2. I don't know. It's 2 cosine of 2x. I don't know. This is... Will this work? Because we'll have... This will be 2 cosine of 2x minus 1. And I don't know if that kind of makes anything better or so. I don't know. That doesn't... Yeah. That's kind of scary. I don't know about that. No, we're not doing this. This is disgusting. And disgusting. We're not taking this route. So, well, silver, what are we gonna do then? Let's see. So this, I don't know. If you're a math nerd like me, this identity looks familiar, right? You might be thinking, huh, this looks like cosine 3x. But I could be wrong. I could be wrong. How do I check if that's true? Well, my emergency backup would to use complex algebra because I have no other ideas. So if you remember, cosine of x, that's a very terrible spacing. This is equal to e to the ix. And because of this, we can have either this to the power of n, which is equal to cosine of nx plus I sine of n of x. And the reason is because of this. N, which is equal to e to the I of xn. This is de Moivre's theorem. So, that's what we're going to be using. Okay. So, but how do we do that? So this is equal to the real part. This is the real part of cosine of 3x plus I sine of 3x. That's how we would write this. And then here, let's see, this is the real part of e to the I 3x. This might trigger a lot of mathematicians. And then we see that this is the real part of, I'm just going to abbreviate this, cubed. Okay, so we're cubing this. Alright, let's grow some balls of steel to express this. So we have cosine cube plus 3 times c square times is, which will not be into the real part, plus 3 cosine square times I square sine square, and the other will be imaginary. Okay, so this is our real part. So I square is minus 3 cosine sine square cosine cube. Okay. Okay. So then this means that if I can clean up some of these nasty stuff. So cosine 3x is equal to cosine cube minus 3 cosine x sine square. Okay, but that don't look like this. Well, let's make sure by turning everything in terms of cosine of x, because we have sine square. We have sine square. We can definitely turn that in terms of cosine x. So I should probably abbreviate this. Right. 3 sine 1 minus cosine square. Okay, and then this is cosine cube minus 3 cosine plus 3 cosine, not cosine square, that's cube. Oh, would you look at this? That's exactly what this is. I knew it. So this, all along, this integral was just secant 3x dx. And so now this is just equal to 1/3 of ln of secant 3x plus tangent 3x plus c. Cool. That's all that is. So whenever if you want to check an identity like this, de Moivre's theorem is very helpful. And utilizing the real part and the imaginary part. Okay? Oh god. Ugh. I'm gonna throw up. I'm gonna throw up. Ugh. Oh god, what do we do here? If we multiply everything in terms, so multiply top and bottom by secant, we get tangent plus 2 3 tangent x plus 4. Does that make anything nicer? I don't think so. I don't know. It's I'm getting just partial fraction. No. Oh god, no. We're not doing that. Okay. Huh. So what on earth do we even do here? We have two things that would be nice in the numerator. Two things that would be nice. So first of all, let me start with a concept. I'm going to change this to green. We're going to look at this at a conceptual way. So in this concept, we have two nice integrals for sine and cosine. Okay. There are these two nice types of numerators that we would prefer to have. We would prefer to have something where well, let me say, just to be more realistic, we have a, alpha, beta. Like those are coefficients, right? Then I would rather have alpha and beta like this, so that this is all equal to 1. Or we can have the derivative of this. So that would be like alpha cosine minus. It would be minus. This would be minus. Minus beta sine. So then this is just ln of the bottom, right? So that's what we would have. These are the two types of nice numerators that I would prefer to have. But how do we apply that here? So now we gotta think like G-main people. So becoming like the G's. Let's see. Well, it's hard to look at it, right? Because we really have to mess around with the coefficients here. So what on earth do we do? Huh? I did it before. I know I did it before, and it's just for some reason now I can't think. Let's see. 3s plus 4c Oh, okay, it's something like this. Alpha, and then plus beta, minus 4s plus 3c, right? And we want this to equal to sine, abbreviate, sine plus 2 cosine. So, okay, so that's where I'm getting. So we want to turn this numerator in terms of this, but we just don't know what the coefficients are, alpha and beta. So that's what we're looking for. So now this is where we use system of equations. So now this is where we use system of equations to find alpha and beta. And we do it in terms of signs, right? So for sine of x, we have 3 alpha. And then for sine of x here, we have minus 4 beta. And we need that to equal to 1. Okay? Holy Jesus. So for cosine of x, we want 4 alpha. For cosine of x here, we want plus 3 beta. Okay. And we need that to equal to 2 cosine of x. Okay. So let me I'm gonna transfer this at the bottom here. Okay. Okay, well now we're going somewhere. Woo! Okay. So to find alpha, I could just do 4 alpha minus 3 alpha, and that would give me, oh no, I'm stupid. No. I want to eliminate one variable. That's what I want to do. Okay. So to do that, you know what? Actually, I would prefer to just do that. Actually, 4 alpha minus 3 alpha. So this gives me alpha. So because I went like that, this would be 3 minus negative 4, 7 beta. This is 1. Okay. So alpha is equal to 1 minus 7 beta. So now that we know that, I'll just go ahead and plug that. Do I want to plug that in? You know what? YOLO. So 3, I'll plug it in here. 1 minus 7 beta minus 4 beta equals to 1. As you can see, I'm not a math Olympiad because I like to play VR chat and socialize. 3 minus 21 beta minus 4 beta, which equals to 1. This is, let's see, subtract 1, that's 2. Shove everything here, that's 25 beta. As you can see, the coefficients are nasty. So we get beta equals to 2 over 25. Okay. Can you imagine if we actually do partial fractions, the coefficients would be the same, like this, and that's disgusting. So now that we have that, let's go ahead and plug it in here. 3 alpha minus, that's like 8 over 25 equal to 1. Oh god. Then 3 alpha is equal to 1 plus 8 over 25. And that's, what's 25 plus 8? 33? Oh, okay, so now alpha is equal to 11 over 25. Okay, so we found alpha and beta. Awesome. So we found this. Okay, so based off of this, we can now see that. Okay, so with this in the numerator, so to make things clear. So the whole purpose of this is to make everything equal to 1. So this would just be alpha. And alpha is 11 over 25. the purpose of this was to do a u substitution. So with this in the numerator, this would be plus beta, which is 2 over 25, and that would be 1 over u. Right, a 1 over u type of integral. And so now, I'm not going to put du because this is like dx du. I guess we can go like this. And so now that we got our coefficients, I probably should not delete that yet. And the reason is because I need that u. Oh, well, I mean, u's right here. Yeah, we can delete this. I need more room. So, now that we have our coefficients, this is now 11 over 25x plus 225 ln of u, which is 3 sine of x plus 4 cosine of x. Oh God, that was torture. But that was very useful. Now that you know how to deal with such things like this, systems of equations, purposely manipulating the numerator in two nice numerators where we can just cancel out and where we could just do u sub. How are we going to simplify this? I need to play around with the inside. Right, x plus 3 minus x plus 2. This equals to 1. Right, there's something with that. Sine of 1 is equal to sine of x plus 3 minus x plus 2. Would that work? Oh! Oh shit! Okay, so I got the idea now. Oh, okay. Let me put this here so that I don't forget what I'm doing. So just bear with me, okay? Just pay very close attention here. This is very sneaky. So we're gonna multiply top and bottom. Well, we'll leave sine 1 out. But sine 1 is equal to x plus 3 minus x plus 2 here. Right? And we got sine x plus 2, sine x plus 3. Okay. Okay, so with that, we can go ahead and express this in sine law. So this is just a constant, so we don't worry about that. We got sine of x plus 3 cosine x plus 2 minus cosine of x plus 3 and sine of x plus 2, and this is all by sine x plus 2 sine x plus 3. Ooh, and this turns out if we split it in two terms, it cancels out, right? This cancels out, this cancels out, and so we end up getting cotangents. Oh wow. So this becomes cotangent x plus 2 minus cotangent of x plus 3. Oh my god! That's very difficult to see, but I'm glad you watched this because now you are aware of this integral. So if you ever compete at MIT or something similar, Math Soc, UC Berkeley, I don't care. This is a disgusting integral that you don't want to come across, but now that you watch this video, you are aware of this, solution. So now we have, so this is just, we integrate this all over sine of 1, right? So we integrate that, and that's just, let's see, the integral of cotangent, that's ln of sine of x. So this would just be ln of sine x plus 2 minus ln of sine x plus 3 plus c. Holy hell. That was that was just chaos. Cool. The trig manipulation just never stops. So we have cosine 8x minus sine of 8x. What on earth do we do here? Huh. What do we do here? So this is just let's see, if we factor, right? If we factor, this is cosine 4 sine 4, cosine 4 minus sine 4. This factors to sine square minus cosine square minus sine square, and that's just cosine 2x, right? Okay, because cosine square plus sine square is just 1, so we just get c4 plus s4, and then we have cosine 2x. But what can we do with that cosine 2x? What can we do with that? What can we do with that? Well, I want to sort of deal with this. Cosine 4 plus sine 4. Now, this is a very common trick in integration B. Like, just this itself is a very common integral. So, to deal with that, to show you, what you do is you split this, c square, and we get 1 minus sine square. And you do the same thing here, sine square, 1 minus cosine square. And now you get cosine square minus s square c square plus s square minus s square c square. Ah, this and this becomes 1 and then minus 2 square c square. Ah, this is just 1 minus sine 2x a half. That's what we have. So this whole thing is 1 minus a half of sine 2x cosine of 2x. Got it. So now that we know, let u equal, let's see, if we let u equal 1 minus half of sine 2x, du is equal to, this is minus, let's see, 2, chain rule, this becomes cosine of 2x. And so now this is equal to a negative of u du, negative u squared over 2. So half of u, which is 1 minus half of sine 2x squared. Very nice. Oh god, this looks weird. This looks awkward. What do we do? So here, we would use the trig identity, the sine law. So this is sine of x cosine of sine of x minus cosine of x sine of x. Okay, but how does this make it any better? So this is an easy integral, right? because it's just u substitution. Let u equal sine of x. Okay, so we'll deal with that later. This I'm scared of, because what do we do with this? What on earth do we do with this? From 0 to 2 pi of sine of x, cosine of sine of x. Huh. What do we do here? So, I'm gonna give you kind of a cheat here. I'm gonna give you a cheat. And the cheat thing is sine of x and cosine of x as well. They're periodic, but what are they periodic at? They are periodic at pi. So, what that means is sine of pi minus x is equal to sine of x, because they're periodic at pi. So, I'm sorry, no, they're periodic at 2 pi. I lied. They're periodic at 2 pi. I forgot to realize that, let's see, sine pi minus, is it pi minus x? Oh shoot, no, this would be negative x, negative sine of x. I'm sorry, because pi, sine pi, let's see, 0, and then you get sine of negative x. You would get sine of negative x, which leaves you to negative sine of x, because sine's an odd function. So, okay, but what do we do with this? So the reason why I want to use this trig identity is because I want to manipulate this bound, and you'll see why, right? If I let u equal pi minus x, then this, well, du, first of all, this is negative dx. So that negative is going to switch the bounds. So 2 pi, so pi minus 2 pi, oh here, pi minus 2 pi, that's negative pi, but by switching it, it'll go here. 0, pi minus 0 is pi, but instead of here, we go here, because of this negative that switches the bounds. And then sine of pi minus u, that's still sine of u, negative sine of u, right? And then same goes for here, cosine negative sine of u, but that's just sine of u, because cosine is an even function. Okay, so that's that. Oh, wait a minute, repeat that. Cosine is an even function. Cosine is an even function, but sine is an odd function. So if this is an even function, this is an odd function, this whole thing is an odd function. And look at this, negative pi, pi, this is all 0. Which means that this portion here is equal to 0. Oh, great. There you go. That's my trick for the day. I just spoiled you guys a very advanced trick. So this is equal to 0. So now we're left with from 0 to 2 pi, let u equal sine of x, and this is sine of u. I forgot I have to change the bounds. Sine of 0 is 0. Sine of 2 pi is 0. What? Oh, that's not my pen. But would you look at that? Sine of u, 0, 0, this is also equal to 0. Right. However, if you're still sus about it, that's okay. You can still leave it. You can still leave it. Right? If you're very sus about this. If you're very sus about this, here, just to calm you down, right? I won't plug it in. Let's just say that this is an indefinite, right? If this was an indefinite integral, right? And this is equal to, let's see, sine, that's negative cosine of sine of x. And then you plug in 2 pi and 0. How about that? Right? Here. I'll prove it to you that this works. 2 pi, sine 2 pi, this gives me cosine of 0, that's negative 1. Right? Minus what? Cosine, let's see, sine of 0 is also 0, negative cosine of 0, that's also negative 1. You see? 0. So this whole integral is just 0. Okay? Most people, they saw this by looking at it in a graph. They literally, they just straight up graph this function. I don't know about you, but I don't memorize graphs, okay? Especially complex ones like this. Like I'm not that kind of person. So, equationally, I do the equational way, which is a lot easier to see, at least for me. Oh god. So, if I didn't teach you that G-main trick, then you would be stuck like the rest of the others. Looking at this, staring at this, that root 3 just tormenting you, I am sorry. Right. Weierstrass, I am sorry. Good luck handling that root 3. So, we're doing the G-main way. In this case, we would multiply top and bottom by a half. I'm just going to put a half here. And then root 3 over 2. Cosine plus a half. Sine here. Okay. Now again, I like to deal with secants. So, I need to find cosine. Now, this is x. Because this is a plus, I would go minus. But then, I need to look for, okay. So it's between either pi over 6 or pi over 3. So, root 3, so this is, we're dealing with cosine, so this would be like cosine, cosine, sine, sine, right? So cosine of what equals root, or I guess, what is this pretty much? What is this? What does this equal? Let's see, cosine root 3, oh, this is pi over 6, right? This is pi over 6. And then for a half, to make sure, yep, this is also a half for sine pi over 6 as well. Okay, so it's pi over 6. Got it. So now that we know that, it's pi over 6, pi over 6. Go ahead and write it, pi over 6. Cool. So now this integral is just a half of secant x minus pi over 6, which is equal, I'm going to write it here, ln of secant x minus pi over 6 plus tangent of x minus pi over 6. Okay, awesome. So this is a very famous, oh, I wouldn't say very famous, but it's a popular integral that would come up in a very competitive integration bee. So, how do you handle something like this? So there's a trig identity that you do have to know. For beginners, I wouldn't require you to do this, but if you want to do like advanced integration bee or like Harvard, MIT, I would suggest you to know this identity, and that is tangent A, tangent B, 1 minus tan A, tan B. How on earth did I know this in high school? Well, it's because I had to write a song about this trig identity, and I used the knife song, the knife song to memorize this. I realized I messed up my identity. This is wrong. You see how when I sang the song, I already knew immediately that this is incorrect. Right? Tangent A plus B equals to tan A plus tan B. All that divided by 1 minus tan A times tan B. Now, if tangent was subtraction, then tan A takes tan B. All that divided by 1 adding tan A times tan B. I promise you, I am not emo, I'm not a psychopath, the knife song was just perfect. Okay. Please don't do the knife game though. I don't encourage that. Please do not hurt yourself. I used a pencil in the video and the math faculty were concerned. But anyways, so now that we have that trig identity, we're gonna go ahead. Let's see. We have tangent 3x. What is this equal to? This is equal to tangent x plus tangent 2x. 1 minus tangent x tangent 2x. So we're going to use this trig identity. And the reason why is because of this. This is what we're going to manipulate. So we're going to shove this whole thing. We're going to shove this whole thing into this trig function. So we have tangent 3x. I'm sorry. Minus tangent 3x minus this long chain we know equal to tan x plus tangent 2x. With this long chain, we can go ahead and manipulate it on one side to the other, right? And so now this becomes tangent 3x minus tangent x minus tangent 2x, which equals a bunch of chain of products of tangents that we originally had. So that's what this integral equals. This is a simple integral. Easy integral now. This is just an easy u sub ln of secant 3x minus, this is just ln of secant x minus a half of ln secant 2x. It's a very long answer, but this all this is. And there you go. Oh god, not another one. So what do we do with this? So through sine x and sine 3x, what can we do to manipulate this? Right? What is this equal to? Well, if you don't remember the trig identity, it's okay. I'm with you. I don't remember the trig identity. So we're gonna see here, this is just a plus b, here a minus b, and this would be cosine, cosine minus sine, sine, cosine, cosine plus sine, sine. And so now we need to subtract this so that we can maintain sine, sine, and cancel these out. So this is a half of cosine of a minus b, which would be 2x, and then minus cosine of 4x. So this is what we're going to be using. Alright, cool. So let's go ahead and substitute this into here. So now that we got this, I'm going to go ahead and turn this cosine 4x in terms of cosine 2x. So this would look like pi over 2. Then we have sine 2x. I'm just going to put 2 there. And in terms of cosine, we have like cosine here. And then this would be like, let's turn this into 2 cosine minus 1. Right. Awesome. So now we let u equal cosine of 2x. This will give us du of sine 2x, well, negative. But if we plug in, let's see, cosine 0, that's 1. Plug in cosine of pi over 2. Cosine, well, it'll be cosine pi. Cosine pi, that's here. That's negative 1. So we get 1 to negative 1. Okay. And that's what that negative is used for, to switch the bounds. And now, don't forget that this is, when we derive this, this would be du negative sine of 2x times 2 because of the chain rule. So we have 1/4 technically. And now this whole thing is just some quadratic equation. So this is like 1 plus u minus 2u squared, right? 1 cosine and then 2 cosine squared. Okay, so that's all this is. And we can actually take that out because that's an odd function. And because of -1 to 1. So this is just 1/4. Because everything's even, we can do symmetry as well with even functions. From 0 to 1, 1 minus 2u squared du. Awesome! So then this is just a half of u minus 2/3 of u cubed from 0 to 1. This 0 is 0 for everything. 1, we plug in 1. This is 1 minus 2/3. So this whole thing is equal to 1/6. And that is our answer. Alright, that actually simplifies very nicely. Our last integral is this crazy integral here. This is a very crazy integral. Trust me, if you don't know what you're doing, this will screw you over big time. So we want to do conjugation. But the question is, what do we conjugate it with? What do we conjugate it with minus here or with minus here? Which way? So the way I would do it is I would probably conjugate it like this. So that in this way we get secant square minus tangent x plus 1 square, right? And then we have secant square of x minus square of this is tangent square plus 2 tangent of x plus 1. That's secant, and then this is all equal to 2, negative 2 tangent x. Okay. So that's what we're going to do. So we're going to conjugate this top and bottom, right? So again, conjugating, we get negative 2 tangent x here. All right. And then here for sine, we're just kind of left with secant x minus tangent minus 1 technically because of the parentheses. Okay, so let me go ahead and make some space here. So now, what is this? To simplify it further, multiplying sine of x to everything, this gives me tangent x here. This gives me sine square over cosine. Or what am I doing? Leave it like this. Tangent x sine of x. And then minus sine of x. Okay. Now this kind of simplifies to just, if we split it in terms, this is just negative 1/2. This is plus sine of x over 2. And then plus sine times, that's cosine. Oh, wow. So then we have cosine of x over 2 dx. Cool. So then this is just equal to a half of, let's start with this, sine of x minus cosine of x, and then minus x. I just kind of factored out the half. Okay, so now we have pi over 4 to 0. Pi over 4, first off, pi over 4, root 2 over 2, root 2 over 2. That's going to cancel each other out. and then we have negative pi over 4 minus a half of 0. Plugging in 0, we get negative 1. So this would be like that. So we have a half minus pi over 8. And this would be our answer. Holy hell! And that's it. That's all the advanced trig manipulation. Now, that was a lot of tricks that we've gone over. A lot of variety of tricks that we can use. But there was a ton of trig manipulation. So I would recommend that after you watch this video, I would sort of replay this video and try the integrals, all the integrals yourself, and try to see if you can remember the tricks. If you can, that's good. That means that eventually, or in somewhat ways, it will just kind of stick to your head, which is what you would want, because you want to be aware of these trig manipulations that you can do in integration B. So a lot that we covered. A lot. So thank you so much for watching, and I'll see you guys in the next part.